Okay, well, so as we discussed, I'll be doing that presentation in English. That doesn't matter, Russian or English. If we'll be doing a QA session after, we can go for Russian if you want. It doesn't matter to me which language we'll be using in there. So I'll try to be a very normal pace in English, just to make sure that everyone gets everything and we are not just rapidly pacing in there. So today I'll be talking about the usage of BERT on medical data, and there are basically three things I want to walk through. So the first thing is adapting the electronic health records. A little bit later, what is it, how to cook that for language modeling. The second part will be on the pre-cooking the BERT to a condition of BHR. Probably I will be pronouncing that as BERT, just to make sure that it's always feasible. And the last thing will be about large medical models. Of course, it's on the fantasies right at the moment. So let's start with that. So going from text to the electronic health records. So the first thing, what is EHR at all? It's basically it's a fancy cascade of tables. And the most important to keep is basically just the right question to ask. There are just too many tables. And okay, so the EHRs, it's basically just a lot of people and everything is centered around them. Everyone has a history of their visits to different hospitals or medics, whatever it might be. And there are various events happening at that point of time. And these events are expressed as a concepts, and concepts are different things, such as drugs, maybe some conditions, and it might be even visits themselves. So basically just have some kind of an encoding that someone has a condition. So a little bit more on the conditions. Conditions are just some diseases most of the time. It's just easier to interpret it this way, but it might be a little bit wider concept. It could be encoded in different way. Here, for example, it's SNOMED vocabulary, and that gives you just some kind of a, let's say, another table that just interprets something and allows you to use some kind of a language for that. So that's basically charts, just lots and lots of tables around patients that just describe their interactions with the hospitals or just healthcare system in general, and they're just composed from different sources. So there are many unsolved problems, and the first one is the importance. There are just too many factors, and you cannot just throw everything at the model and expect it to work. So usually what you do is starting with only conditions, so like diseases, as we discussed, and scale up from it. But conditions, even on their own, there could be like 20K features, and mostly they're intersecting, sometimes they're screwing up data, and you need to filter that out. But the problem is you cannot just, crumb the numbers and get everything you want. Probably you need some medical knowledge to throw away something, maybe adapt somehow, and basically then start iterating. So that will be like a central topic of what we'll be discussing. Everything is about the medical knowledge and iterating by the small steps. Otherwise, everything is breaking up and it's very hard to figure out why. So the second thing here is a problem of errors in the data. The problem is very trivial. We don't have a possibility to really influence how medics or whoever collects the data do that, because most of the data sets are collected by hospitals and we have no influence at all, I don't know, on the UK or the US systems, most of the time at least. So many problems like measurement units could be off. They could be just in a very different scales. There might be disappearing conditions. So sometimes you have diabetes and the next day you don't. What does it mean even? And the missing records, sometimes you're going to a different country, you're getting your records somewhere elsewhere, and you're just suddenly getting some kind of a disease. Who knows why and how to predict that? So that's why you need to really look through the data, as always in the data science, of course, and figure out what might be wrong. There are many things that could go wrong in the medical data. And then unfortunately, most of the time, you should spend a lot of manual time of the laborers. And it's not really good to plan everything for the doctors. It will be just overly expensive. And as of now, there is no real good automated solution for that. People just do the brute force. I mean, the analyst maybe consulting with doctors a little bit, trying to figure out what are the problems. So there will be a few similar slides, but with a different picture, just to give you a few examples. So on this picture here, what we have is the cholesterol level. And what you see is pretty normal distribution, but you have a lot of zeros, like a lot, because someone is just, for example, they're just making analysis, but for some reason they're including that this kind of measurement is just zero. And that screws up the data a little bit, but it's easy to fix, of course. In some cases, it's not. It might mean something very important. And the second thing we can see here on the distribution is the lower part. So people, most likely, it's something like a different scale. And there is this separate distribution for a different scale happening at different parts of the distribution. And that's very interesting because you need to somehow disentangle that, understand what is the scale. Maybe it's UK, maybe it's European Union, maybe it's something different. Why do they use something different? And it might be even percentage points, and that's another story. The second thing, for example, hemoglobin, right? Again, we see zeros. There are just lots of zeros, maybe for no reason. There is a small distribution of outliers on the small scale. It seems like we have some kind of different scale in there. And then we have a very interesting part in the distribution. So it's somewhat normal, skewed to the right, long tail, and it's kind of fine. Probably not everyone does the hemoglobin tests all the time, but you can see a very interesting pattern. So every time you have some kind of a gap in the distribution, and these gaps are usually kind of combined with something on the bottom, like a separate distribution. So someone is given, again, different measurement units. Moreover, you can see on the left of these gaps, all of the time, there is some kind of increase, kind of rough increase in the amount. And that's something that screws up the distribution. To work with that with some classical methods. So the next problem we face in medical data is anomalies. And well, basically, it's easy to confuse an anomaly for another error. So it's good idea to run anomaly detection on separate features in temporal order. What does it mean? Basically, you have a patient, but they could have kind of different measurements or whatever in time, some different units or whatever. And if you see the anomaly in temporal space, that's one thing. The second thing is you can have an anomaly in population distribution. So it's like everyone in the population, they have some kind of a distribution for at one point of time, but you see something is wrong. That's not the case when you can try to fix something. And what we see here is a very interesting pattern on the picture. You can see that it's more like a kind of a stairs. So it's like someone was trying to shift all the time to the left or to the right to some specific measurements, just to simplify maybe the job for them or something like that. So many reasons that why it could be. Again, we see the same thing, like a very small distribution on the left plus extra distribution, which lies under the somewhat Gaussian distribution. And usually it's not that easy to run some complex anomaly detection and all of that, because it will just screw up. And usually what you do is use a mixture of shallow detectors, because it's much easier to fine tune them, modify some small parameters and try to play around that. What happens next? Again, anomalies. That's a very spectacular case of people trying to really move something to specific measurements. That's the same story, and that's just spectacular. So I think the last problem, and in my opinion, the most important, especially for the BERT and stuff. So what we have in there is the zero or a high demand. And it's better to start with the picture, I think. So this picture is basically showing you the distribution of distances between visits. So basically the first column means that if you went to the doctor, then there is a very high probability that you will go to the doctor tomorrow. And then the distribution goes down. So if you're going in a week, in 2 weeks, in 3, 4, it lowers down. But what you can see, it's interesting, is that you do that every week. And that's because of the formalized system, most likely. So when you go to the doctor, it tells you, okay, come either tomorrow or in 1 week or 2, or maybe 4. And there is another event here. What happens when you go to the doctor? Probably you might be diagnosed with something, but most likely not. And you went for the first time, a very huge column, but the second time, most of the people, they're okay. They're not diagnosed with something, they just go home and never go back. Well, at least for the near future. But some part of them is going for the next week, something is wrong with them. And that might, well, happen every week in general. So that's what you see on the graph. So that's basically a problem of zero or high demand, always iterating. And it's quite hard to work with that with regular time series approaches. And sometimes it's even easier if you want to start modeling and you don't know where to start, how to solve the time series in your case, then it might be good to really ignore the temporality and try to work without that. Just represent people as some kind of a set of features, not in time, just features. So the same thing on the graphs, the same slide. You can see the same distribution, just zoomed, and you can see it around 140 to 220 days. And you have a very interesting peak in a half a year. So that peak, of course, when the doctor says to you, okay, you have a serious illness and you need to come in half a year just to double check that everything is good. I don't know, heart disease maybe. And then there is the same story that in a week, maybe some proportion should go to the doctor and see if they still have a problem, if it's worse, etc. And you can see that the difference is smaller. So when we are trying to validate people in a half a year, there is higher probability that they have developed really something and they need to go for the second visit. Or maybe it's just the nature of these diseases that you need to go for the second kind of trial. And the same thing basically for 1 year. So you can see again the peak, and the people are going in a week almost the same amount of time as they do just in 1 year. And on all of these slides, what you could see is that every time around this day, there is a small kind of increase in probabilities. So people sometimes are not able to go to the same day. Most likely it's more or less operational problem. So it's like the doctors just cannot make a visit. So that goes us to the second part. So that's BERT to B chart. So what we see here, so the guys made such a paper, BERT, and that's the idea of kind of widening the idea of BERT to EHRs. That's where the name comes from. And there are not that many new ideas, so let's just briefly go through them. So what they have is they represent every visit as a list of some concepts, and that just builds up the whole history in temporal order. And that's how you work with that. You have some separator tokens introduced, which are used to kind of separate visits between themselves, just to make sure that you understand that's a different day. And it's the same way as in BERT, it's for the sentences, for example. So we take this idea further in order to scale it up. So they kind of propose to scale it up from just conditions to measurements, medicines, etc. But they don't do that in the paper. So we extend the idea and just propose a way to do that. So introducing some special tokens that might represent that, okay, there is a condition or a set of conditions, or there is a medication, just to simplify things for the BERT. But it's not the only way you can try to solve that, and maybe it's not the best. So another thing that comes to mind is inside of the positional encodings and embeddings, what we have in there is, well, the first, okay, adapting to irregularity. That's a different story. But if we continue the idea, what we can try to do is to kind of integrate the age of people in there, as they do in the BERT. They try to at least add some temporality, but they don't handle these differences in how often or how sparse the visits. So that's what we plan to do. So we try to include date distance between events via positional encodings. And what you can do to, let's go to the previous slide. So what we can do to really separate different conditions, measurements, etc. We can also add that to the encodings, just to simplify the work again for the BERT, to differentiate between, is this condition, is this medication, because it might be very different, but not numerically. So what goes next is, of course, a pre-training of all of that. MLM, NSP, and all of that things, they're all kind of adaptable. MLM could be adapted to many formats of the data. It might be graphs, even molecular data like voxels. And it's pretty easy to do on the clinical data if you represent it as a sequence. So you basically just mask something or exchange something and just ask to recover that. For the NSP, there are many flavors of that in different BERT-based models. And in our case, usually if you want to add some tasks or modify some tasks, usually you do that on the NSP somehow. So for example, in our case, it's prediction of conditions during the future visits, or it might be not the exact condition, but just the presence of something or addition of something. So just to simplify things for the pre-training. So what goes next? Our goal was to design a highly informative embedding space. So we do some analysis and get some insights from that clustering and all of that. But the problem is usual BERT problems. They're not really suitable for that. And we need some kind of specific architecture problem task to solve to train the BERT in order to be useful for that. So what we orient at is BERT. So this BERT is sentence BERT. And the idea is that they use the SNLI dataset. What they do, they basically introduce two sentences, and there are two BERTs that are just C and Is. And they try to understand what is the relationship between them. Either it's entailment, neutral, or contradiction. So basically, in their case, it's very simple. So basically, you have a sentence, and there is another sentence that might contradict to it. So someone is doing something, but at the same time is doing something, then it's a contradiction. But if it's entailment, then this kind of events are close together, they're meaningful to be done together, and that's fine. Or it's neutral, meaning that there is nothing related to the question. In our case, to adapt that to the medical data, it's not that easy. So you cannot just take these statements and use them on a condition in some very slightly changed form. What you get is very obvious interactions and dependencies between the conditions or diseases. And that's not the way to go. And right now we're in the process of trying to adapt the task to what we have at hand. Probably the most leading hypothesis here is trying to take some other tables, for example, medications, let's say, and try to find a correlation between some conditions through the medications and build on top of that the idea of the entailment or contradiction. So basically trying to figure out a way how two conditions could be entailed by some medication or any event that could be in the EHR. So that's the idea. It's not yet done. It's in the process. And that's kind of a complex stuff. So that leads us to the not very large medical modeling. It's not yet there, but that's what we get. So the medical embedding space is just a space, as always. Nothing special, it's just a space we can work with, build something on top of it, try to solve some task based on the embeddings, etc. But in the medical space, what is very important is that at least interpretability, not even explainability. And usually you need to reduce dimensions to see something meaningful. So you just need to find a good way to reduce the dimensions. Otherwise, it's very hard to find something interesting and meaningful that could be deciphered by the magicians. So modern models, they're kind of capable of computing these useful manifolds, but we are not yet there to combine them with anything else. Well, you could, but usually you get a lot of noise. And that's why most of this presentation is based on the idea of what to do with the data, how to prepare that for the transference, and how to go to the large models. So on the right, we have a very nice picture from BERT again. They have a very interesting distribution in this embedding space where they have something like tinnitus and hearing loss close together. That's interesting to have. Or for example, on the right, you have yellow dots with the depression, anxiety, and alcohol problems. And that's very interesting because it's not that obvious connection. I mean, we know that they are connected, but it's not directly connected. And the same thing with the asthma and all of the other stuff. We see interesting kind of insights in there. Maybe they're very obvious to be useful right now, but we see the progress. So regarding the explaining or interpretation of the dependencies, Well, one of the things is attention mechanism, right? So it might guide your kind of efforts, but it might also mislead your efforts the same way as it was with the gradient methods. When you try to kind of interpret the results, but you're getting just the information where the model looks. That's what you get. And you don't get any causality, and it might be looking in the wrong place and initially, and it's very hard to figure out that it's looking in the wrong place. So be very critical about that. And because of that fact, it might be used to rapidly prototype something, but not really kind of, don't make it a basis of your R&D. That might be crucial, that might just ruin what you do. So in the long term, there is such a thing as SHAP. Right now, SHAP is a combination of Lime and Shapley values. And long story short, you can read about that very rapidly, but long story short, the idea is that you're trying to learn very simple models on top of your very complex models. That's Lime. And Shapley values just try to kind of figure out which features are very important for the prediction of some cluster or a class. And that's what we get. You get some kind of a distribution for different features that might lead to the prediction of what you have actually embedded and clustered. So that's something you can do, and you don't need any fancy hats on top of the BERT backbone. And basically the last thing, what I would recommend in the end, so there is a lot of fine tuning and it's very easy to screw up. So there are just a bunch of approaches in NLP that you could reuse and adapt and all of that, but you need to be very careful. You need to have someone to critically assess that from a medical standpoint, because it's not that simple as with the language right at the moment. There are no predefined standards for that. At the same time, high chances, if your product, it could be anything, you should really hire someone. I mean, external specialists are great, but if you're really planning going to just hire someone, and ideally someone with a data science practice at the same time, you don't need very fancy, I don't know, double PhD guys with the biology background and computer science background at the same time, but you need at least someone with the analytics background, or maybe at least a few courses in the medics background, doesn't matter. So there is no default way to validate all of that. And even if you do that computationally, figure out a way, and there is a standard practice, it might take years and years before you can prove it in reality and make it usable at all. So what I suggest in the end, and that's the whole topic of the whole presentation, just do that gradually, increase the complexity gradually as any experiment, just control some parameters and change a little bit as you do with the fine tuning of parameters or whatever. And every kind of table that you use and you kind of extend the solution to it, it might have the same anomalies or errors or whatever that are working in a very different way. And that requires an eye of a medic. So that's another machine learning story, I say. So the data is the key. Again, if you have garbage, you have garbage on the output. So that's it. And thanks for your time, guys.
Спасибо. Мне кажется, очень мощный и хороший доклад на завершение. Не против, если по-русски, собственно говоря, зададим вопрос?
Да, конечно.
Я начну, наверное, с такого глобального. Я вот 4 года работаю в медицинском ML, и у меня все это время есть две мечты, если так можно выразиться. Одна – это мультимодальность, то есть вот мы работаем с медицинскими картинками, и обычно у нас нет никакой больше информации о пациенте. И вторая мечта – это какое-то вот извлечение нового знания. Не просто учиться на разметке врачей, а что-то вот новое понимать о людях, какое-то медицинское знание. И вот мне кажется, что это крутое движение в обе эти стороны, поправь, если не так, потому что, по идее, там, несмотря на то, что ты сказал, что медицинские записи – это таблицы, сюда же, наверное, можно заэмбедить там и те же рентгены, картинки какие-то и что угодно, да. Это вот первый вопрос, там, есть ли какое-то вот движение в этом направлении. И второй, ты вот указал на то, что, да, действительно, пока там коннекшены какие-то, может быть, в основном банальные, но уже есть какие-то непрямые. Сможем ли мы, как ты думаешь, такими моделями вот действительно какое-то новое знание извлекать о людях?
Ну, во-первых, я бы сказал, что доменное знание для меня это тоже такая, скажем, влажная мечта, как это говорится. То есть, когда мы можем совместить несколько модальностей данных, это становится очень интересно. Насколько я помню, Facebook делал это, очевидно, не для медицинских данных. Мне кажется, много кто начал уходить в эту тему. На медицинских данных у нас пока что такого нету. То есть в теории, да, конечно, можно. Проблема в том, что и HR – это такой вот отдельный мир, очень сложный, для которого пока что вот нету чего-то прям сильно работающего. То есть даже если мы условно можем хорошо применить практики из CV в медицинских снимках, то для табличек все сильно сложнее. То есть это отдельная прям история, которую еще как-то надо синтегрировать со всем остальным. Но да, конечно, то есть все движется к тому, чтобы эмбеддить разные пространства во что-то похожее совместно и пытаться с этим работать. Вот. По поводу второго, насчет поиска всяких инсайтов, которые могут быть неочевидными, я думаю, в целом в биоинформатике, в медицине многие вещи строились, я бы сказал, на интуитивном уровне достаточно долго. То есть даже биоинформатика – это очень такое свежее направление. И когда мы сюда внесли аналитику, а это было не так давно, может быть, 20 лет назад, скажем, да, а какие-то прямо сложные методы аналитические появились только лет 10 назад и вошли в практику, может быть, 5, может быть, чуть раньше, то здесь очень много потенциала для того, чтобы что-то интересное открыть. То есть человек, он очень ограничен в том, какие инсайты он может выжать самостоятельными усилиями. Поэтому мне кажется, что даже если модели не дадут чего-то вот прямо космически нового, чего мы там прям не ожидали, но они как минимум позволят найти, возможно, даже какие-то наши байесы, какие-то наши ошибки, и дать какие-то минимальные наводки, какие есть вот интересные зацепки, куда можно посмотреть. И то есть это естественная история, мне кажется, и для медицинских снимков, что такие системы, они не заменяют человека с медицинским образованием, они не заменяют специалиста, но они ему помогают, они гайдят его процесс мышления в нужную сторону, позволяя ему получить что-то быстрее и, возможно, лучше.
Да, я согласен. Кстати, про байесы прикольный поинт. Мы даже думали в том, что можно было бы даже конкретным, например, специалистам давать какие-то рекомендации о том, что у них вот есть определенный байес в том, как они там, не знаю, ведут осмотр или снимки интерпретируют и так далее. Антон, есть ли у нас еще?
Хотел еще спросить, но у меня такой уже больше вот конкретно по слайдам. Вот вы используете BERT и передаете в него такие последовательные кусочки. И каждый кусочек – это как бы один поход пациента к врачу, верно?
Если считать, что есть один поход, это какой-то кусочек, мы комбинируем несколько таких походов, там получается, допустим, 512 токенов, то как бы да.
Подожди, 512 токенов, это, то есть это на них разбивается весь поход?
Не
Я
совсем.
просто, у меня такой интерес, что кажется из этой схемы, что это будет работать только на каких-то периодических историях, то есть когда человек периодически ходит к одному врачу лечить одну болезнь.
Ну, ребята там вот и пытались.
Да, мне тоже кажется, что, по крайней мере, моя интерпретация, да, мне тоже кажется, что если человек ходит к разным врачам и, допустим, в разные клиники и так далее, в разные места, то есть определенно есть байсы в ту или иную сторону, просто за счет оборудования, за счет врачей, за счет клиник и так далее. И от этих байсов как будто, пока что невозможно убежать. То есть здесь скорее есть такая история, что есть байсы, с которыми нельзя смириться, а есть байсы, с которыми можно смириться.
Окей.